Okay, here we've got a couple of questions relating to the photoelectric effect. Here's the formula. This is Einstein's equation for this. The maximum kinetic energy of electrons is equal to the incident light. So this is the electrons that come out. The energy of the electrons is equal to the energy of the light that comes in minus the work function, or the energy needed to escape, the escape energy. Escape energy needed. Alright, so there's a light source, makes light, filters so they can change the colours just like we did in class, and the tube here, which has the potassium plate, the light hits that, the electrons escape, try and make a circuit, but what we can do is we can put an opposing voltage to stop them from making that circuit, and we can measure that voltage. So explain in words what each of these things mean. E, K, max, F and W in the equation above. Your explanation must show how each term relates to the experiment in figure 3. Alright, so EK max is the maximum kinetic energy of escape electrons, of escaped, or maybe a better word would be ejected electrons. Now I think, I haven't got this all on one page, I think they're only worth 1 mark each. So I don't think I'm going to talk about the voltages for this at the moment. Right. F is frequency of the light. Now this emits light of all different frequencies. It's a filament lamp by the look of it. So it's really important you talk about the light, or the frequency of the light after the filter, or the frequency of the light that went through the filter. Because that really says it's, you're talking about the red light or the blue light, whatever the colour the filter was. This one. And the other one I wanted us to explain was W, the work function. W is the work function, which is the minimum energy needed for electrons to escape. Remember, I'm just going to use this B ejected like that from the metal. Alright. So this is the graph. We got a very similar graph in class when we did the experiment. What they've done is they've measured the actual voltages for different colours, the frequencies of the colours of the light, and they've plotted the voltages that they get when they did this experiment. So from the graph above, can you determine Planck's constant and the work function of the material? Now remember, this graph relates to maximum kinetic energy. Kinetic energy max equals HF minus W. This equation is this line. It's a straight line with HF is this is your mx plus c, and minus W is the intercept down here. So really, if we look at this mx plus c, h is the gradient, Planck's constant is the gradient, and W, the work function, is the intercept. So we'll do the intercept first, that's the easiest one. The intercept happens about 1.5. The answer is not negative 1.5, okay? Even though it goes down here through negative 1.5. If you were to put negative 1.5 as the work function in this, you get kinetic energy equals HF minus negative 1.5. minus a negative is a positive, so you get kinetic energy equals HF plus 1.5. And that graph would look like starting here and going up like that. But it doesn't, it's down here. So because I've already got the negative in the equation, the work function is a positive number. So that's that one easy. I'll write the gradient now. Let's just pick 2 points and we'll go from there. So, well, this is an easy point here, and this is an easy point here, because they go through 2 lines. So gradient, Planck's constant is the gradient, which is rise over run. So how much does it rise by from going from here to here? It rises by 1 voltage, 1 volt. That's 1. And how much does it run by? I'm going from here to here, which is the run. It runs by, from 3 to 5, so it runs 2 by 10 to the 14. And that equals a half by 10 to the minus 14, which equals 0.5 by 10 to the minus 14, which equals 5 by 10 to the minus 15 electron volt seconds. The units are already ready to go because the top unit was electron volts, the bottom unit was, that's where the electron volts comes from, the bottom unit was hertz, and a hertz is equal to a per second. That per second goes to the top and becomes a positive second, so that's where that comes from. And if you look on the formula sheet, you'll see that the Planck's constant, actual Planck's constant in that unit is 4 by 10 to the minus 15. So we're pretty much on it with that. So it was a good experiment and quite accurate with the values they got. Cool. And then the last one in this series of questions. This one. Okay, with the filter for a particular frequency of this, Kirsty and Adrian now double the intensity. What will this have on the maximum kinetic energy? So when we answered question 2, I think it was, in this 2009 series, about why the photoelectric effect shows that light has particle properties, changing the intensity doesn't change the maximum kinetic energy. So it has no effect on this. However, doubling the intensity means more photons. More photons means more electrons. They don't have any more kinetic energy. The kinetic energy of these electrons is the same, but more electrons is more current. So there's going to be an increase for this last one.